somehow.
Right. He just has to start talking to them.
Oh, I see. Okay, let's start today's seminar. Today it's our great pleasure to have Professor Randy Lewis from York University. Randy got his PhD from University of Toronto in 1995, and then he was doing postdoc studies at the Jefferson Lab and the Triumph. If you don't know Triumph is Canada's Particle Accelerator Center. They have a beautiful campus in suburb of Vancouver. And then he moved to Regina University as a faculty, and later joined the York University. He has been doing works on using lattice QCD to study standard model physics, exotic hadrons, and beyond standard model physics. And in recent years, he has been leading some pioneering work in quantum simulation for lattice gauge theory. And today, he's going to tell us about the triamond lattice for SU2 lattice gauge theory. Randy, please go ahead.
Thank you very much. And hello, everyone. It's great to see you. Hopefully you can hear me well. And I will try my best to hear you, but don't hesitate to interrupt and get my attention if you need to. What I'd like to do is tell you about some work I've been doing recently with a graduate student. Ali Kavaki is with me in Toronto at York University. And here's the preprint at the top of the screen in case you want to find more details. What I'd like to do is lead us through a little discussion with three parts. Part one will be a calculation we did using a mitigation technique for imaginary time evolution, which we think leads to an interesting result. And then I'll move on to part two of the talk, where we introduce the triamond lattice as a way to go to three spatial dimensions. And part three will be a specific example of using the triamond lattice just on one unit cell. The goal here is to gain some intuition for a lattice that might not be familiar to us and help us get more comfortable with how this lattice might get used in practice. So just to start, let me say what everybody in this audience already knows and thinks about. Lattice gauge theory has been a wonderfully successful tool for a long time, and it will continue to be for a long time to come. And it's been so successful, it would be great if it could do even other things that it maybe isn't natural for in its traditional approach. And quantum computers offer that opportunity. So I listed three preprints that appeared recently. I was not involved in any of them, but several of you were. These are very exciting preprints that show just what kind of step forward can be taken. These, for example, are talking about real-time scattering of hadrons in various models. And this is just the kind of thing that makes people excited about quantum computers. So for the very first step in any calculation of this type, one would want to prepare the background in which the physics happens. And that would be the vacuum for the gauge theory, an interacting vacuum, not just the bare vacuum. So how could we prepare an interacting vacuum? A couple of methods come to mind. One would be the variational method. You think up an ansatz with some free parameters, and you vary the parameters to find the minimum energy that that ansatz will allow you to reach. And that would be your estimate of the interacting vacuum. Another possibility would be imaginary time evolution, something that's used very routinely in lattice gauge theory. This would, in principle, get you exactly to the interacting vacuum, but on a quantum computer, there might be many entangling gates involved, and it might be a noisy way to go, at least at present. So we wanted to take a look for ourselves and see what imaginary time evolution might look like on an IBM quantum computer, just in a small instance and using a mitigation method that's easy to use and available today. So to begin, if we look in the top left corner, it's the standard story. Any state can be written as a linear combination of basis states. Choosing the various coefficients is what allows you to get any state you want. And each basis state is weighted generally by a phase factor containing the time step and the energy of that basis state. Usually there would be a factor of I here, but since we're using imaginary time, the I cancels with the imaginary time. And now we have these very convenient exponential damping factors. So that if we wait a long enough amount of imaginary time, all of the excited states damp away exponentially so that the result is dominated by the ground state, which is the interacting ground state, the very thing you want to find. Suppose we run code then with just a very small lattice, 2 plaquettes, sharing a common link in the center. Skipping all of the details, here is one time step, one step of imaginary time for this lattice. And if you want to use multiple time steps, just have multiple copies of this circuit end to end. So I'll show you the results that we obtained. The horizontal line here is the correct answer, which of course is easy to obtain classically because it's a tiny system. You can see, in fact, that our circuit is just 2 qubits. So it's a very, very small system. But it's interesting to see that when we run on IBM Lagos, publicly available until recently, we actually never obtain the correct result, even just for this 2 qubit system. We start at a height of 0, that's the choice of our initial state. After one step of imaginary time, we get closer to the dashed line, but then more steps, we hover around the same point, and then the data start wandering in the opposite direction, further and further away from the true result. And you might say, well, of course, that's what happens because we know we have to apply mitigation methods on today's hardware. And sure enough, if we apply mitigation, everything works extremely well. From the initial point, we move toward the dashed line. We're there within just a few steps of imaginary time. And if you keep going to many steps of imaginary time, you're still there very robustly at the correct result. And so I just wanted to give a couple of slides to say a few more details of how this was done. One slide about imaginary time evolution on a quantum computer, and then one slide about the mitigation method.
Randy, can I ask you a question about the previous plot?
Absolutely.
So the error bars here, are they completely dominated by the statistical uncertainty, or there's some additional uncertainty in the error bars?
Good. The error bars on the top data set, these are statistical error bars, and you can see that they do not capture any sort of systematic error because they're nowhere near the true result, and they're very small error bars. But now here we have larger error bars, and these came from using the data that you see above and rescaling it by the mitigation method. And so these error bars capture that rescaling, which is part of the mitigation method.
I see. So the error bars grows at a later time because that rescaling factor becomes bigger. And I think of that way. I see.
That's exactly right.
I see. Okay, thank you very much.
Yeah, that's perfect. You're anticipating what we can talk about again in the next couple of slides, but you're way ahead of me. You're exactly right. Yes.
I see. Yeah, thank you.
So let's take one slide to remember how imaginary time evolution can be done on a quantum computer. Our reference will be this paper from already 5 years ago now, I guess. It's worth thinking about because, of course, quantum computers perform unitary operations, but imaginary time evolution is not unitary. So it's not natural or obvious, perhaps, how to do this. But here's how the story goes. If you have a certain state at time 0, it may not be a normalized state, but if you pull out the normalization and name it R by yourself, then what's left over is a normalized state that you could prepare on the quantum computer. And then, if you want to evolve that state to a later time, you want to take the initial state and multiply or act on it with this operator, which is an exponentiated version of the Hamiltonian. Again, this is not a unitary operator. However, whatever the result is of performing this operation, it must be some normalization factor, R prime, times a unitary operator acting on the properly normalized state from the preceding time step. So the question is, what is the expression for R prime, and what is this operator capital A? It turns out that R prime can be calculated from the previous normalization factor by measuring on the quantum computer the expectation value of the Hamiltonian. And capital A can be written as some general linear combination of Pauli strings. Notice that ours is just a 2-qubit calculation, so we only need 1 Pauli or 2 Paulis per term. But notice that we didn't write down all possible 1 Pauli terms and all possible 2 Pauli terms. We only wrote down the ones that have exactly 1 Y gate in it. And that's important because what we're trying to do is imaginary time evolution. There is no I up here in this exponent, and we want to write it as a unitary operator, which does have an I. So our capital A should have exactly 1 I in it. It should be imaginary, and that's why we need exactly 1 Y gate in every term. But it remains to be decided what all these coefficients are, these small a's. And this is part of what is run on the quantum computer in doing imaginary time evolution. So I didn't write down all the details on the slide, but I can just say in words, what you'll want to do is calculate the expectation value of the Hamiltonian, calculate the expectation value of every one of these terms in A. You also want to calculate the commutator of each of these terms with the Hamiltonian, and you want to calculate every cross product of A with the conjugate of one of these other terms, one term with the conjugate of the other. So there are a lot of things to calculate, but you can orchestrate to have many of these happen with a single circuit. And we did all of that, and the results are the plot that you saw. But let's give one slide on the mitigation method, of course, because it also had an important consequence for the graph. So our version of mitigation, and of course, many of you have been doing similar things also in your studies. Our version is to take the physics circuit that we want to calculate, which is imaginary time evolution. And then we want to also run a separate circuit, which is our mitigation circuit, and it looks exactly the same as the physics circuit, except that in the second half, we'll just flip the sign of time. So whenever the physics circuit takes 10 steps forward in time to its final result, the mitigation circuit takes 5 steps forward, 5 steps backward, and arrives at the starting state, which is the state that the user chose. And it's a very easy state where we know all of the correct answers. And so by running the quantum computer and comparing what it actually gives to the known correct answers, we've learned something about the errors that are happening in the quantum computer. And then those can be used to rescale the physics circuit because it's essentially the same circuit except for the minus sign. There is randomized compiling that happens for all the C0 gates because you want your noise to be as incoherent as you can make it, and that's part of the process. But the end result is that if you wanted to calculate a single Pauli expectation value, because, say, that's one of the terms in your Hamiltonian, you would measure that directly in the physics circuit, but then you would also run the mitigation circuit with a single Pauli. And this ratio is what would be the mitigated result. And if you have a pair of Paulis in your term, you'll calculate that on the physics circuit, but then you'll rescale it with what came from the mitigation circuit. So we do this for each of the terms in the Hamiltonian, which you see at the bottom of the slide. And it led to the graph that we've already seen. The only new thing I put on the graph now is this dotted line, just to point out that the unmitigated results, they were not just aimlessly wandering away, of course. They were asymptotically approaching the pure noise result, which is simply this constant term in the Hamiltonian, 21/8. Once you lose all of the calculational power of the quantum computer, then each of these terms is just having an average of 0. And the result is 21/8. So as you were anticipating already, it is this gap between the unmitigated results and the dotted line. This is the gap that's telling us about rescaling. And it's that information that gives us these points with their error bars growing that are reliably staying at the true value for as long as these little data points are significantly separated from the dotted line. Okay, so we just like this as a nice plot that shows the power of mitigation today. Even something like a 2-qubit calculation, which never gets to the correct answer, suddenly with simple error mitigation does solidly get to the correct answer. That's nice to see, we think. But maybe I'll go on to part 2, and feel free to drag me back at any point if you have questions or comments in mind. Part 2 is this question about the triamond lattice. So actually, again, I want to start with things that you have done in your group. The hexagonal lattice is something that we found very interesting. If one were going to do physics in 2 dimensions, it might seem natural to write down a square lattice, and it is in many ways, and this is often very convenient. At any site on the square lattice, there are 4 gauge links touching the site, and they can be labeled by their quantum numbers. J1, J2, J3, and J4, for example, in SU2 gauge theory. But that doesn't completely specify the state, because at this point, the combination of 2 of these links, J1 and J2, using the usual rules, for example, of adding angular momentum, that could be the sum, J1 plus J2, or they could add up to the difference, J1 minus J2 in magnitude, or any integer step in between. And so we would maybe want to do some point splitting at this vertex and keep track of what the sum, the SU2 sum of J1 and J2 actually is, so that we can fully define what we meant by this picture and which state we were talking about. And of course, we'd have to keep track too and make sure the user knew, were we adding J1 and J2 together? Or were we adding J1 and J3 together, or some other pair? We could make that convention, provide extra qubits to give the extra information, and then we would fully know what basis state we were describing. On the other hand, if you use a hexagonal lattice, then every site is only touched by 3 links, and simply giving the J values provides all the information that the user needs, because J1 and J2, in this case, add up to J3. They must, by Gauss's law, which says that all of the incoming color charge adds to 0 at this site. And so you might ask, well, can we do the same thing in 3 dimensions? Since it works so well in 2 dimensions, one possibility would be to add extra gauge links coming out of the page or into the page. So that's the 3rd dimension, making something that looks like a honeycomb that bees would build. But of course, if your extra link comes right out of the vertex, then you've got more than 3 gauge links at your site. Or if you have your link coming out somewhere along one of these line segments here, one of these links, then the one going into the page has to be beside that one. And suddenly you lose the nice symmetry that you had with the hexagonal lattice, which is so symmetric. So what can we do in 3 dimensions? Is there a nice solution? And it turns out that there's really a unique option that maintains maximal symmetry in a certain sense and fills 3-dimensional space while keeping just 3 gauge links touching each site. And that's the triamond lattice, or it goes by the name of Lavis lattice or K4 lattice. It's called various things. One way to think about it is to start with a tetrahedron. I've drawn one here on the slide. It has 6 gauge links or 6 sides, and we've shown them in 6 different colors. So we've got a red and a green and a blue. They form an equilateral triangle. And then you've got cyan and magenta and yellow rising from the corners to complete the tetrahedron. And if we use the standard Cartesian coordinate system, where I hat points out of the screen, J hat points to the right, and K hat points up, then red, green, and blue are just the difference of those unit vectors. And cyan, magenta, and yellow are the sums of the unit vectors. So, of course, it's very, very easy to write down those 6 vectors for this tetrahedron. The triamond lattice is made of these same 6 vectors, but they're not in the shape of a tetrahedron. So what we need to do is just translate them through space to be in a different location without rotating them in any way. So I'd like to try to guide you to understand how this works by playing a little game here. Hopefully this works. If you see a blank screen with a tetrahedron on it, we're doing well. And what I'd like to do now is take the green and the yellow links and just slide them along the red link. Hopefully that worked. And now I'd like to take the blue and the cyan and slide them along the blue link to the same vertex. And finally, I want to do one more thing. I want to take the cyan and the magenta and the yellow and slide them outward. We haven't rotated any vectors. We have the same vectors that came from the tetrahedron, but now we have the fundamental building block of the lattice. The triamond lattice is just many copies of this building block, not rotated from each other, but just put side by side. Notice that there are 4 vertices or 4 sites in this building block. We find it convenient to give them colors as well. So there's one right in the center. We think of that as a white site because it's touched by red, green, and blue, and red, green, and blue together make white. Notice that the red, green, and blue links lie in a plane. And notice that they're exactly 120 degrees apart. We're looking at it in perspective here, but if you imagine looking straight down on the plane, you'd see that they're 120 degrees apart, forming a nice symmetric pattern. Every single site on this lattice has that pattern. At every single site, the 3 links arrive in a plane, and they're 120 degrees from each other. For example, back here at this blue site, there's a blue link touching it, and there's a cyan link touching it, and there's a unique location where we need the other link. It's going to come in the same plane, 120 degrees from the 2 you already see. So that tells us where the next building block needs to go. So if I just zoom out so we have some more space, then we can put in the next building block. There it is, touching the blue site as it needs to. But then, of course, we also need one for this site. Let's put that in. And we also need one for this site. Let's put that in. And just keep putting these things in exactly where they need to go. It's all unique. And after a while, you notice I see a unit cell here. If we could sketch it as a cube, you notice that the unit cell is very simple. There's a white site at every corner, and there's a white site right in the center of the cube. So I didn't really have to go through any of this business with the tetrahedron. That was just for me to gain some intuition for what we're doing. All you have to do is build a regular cubic lattice and put white sites at all the corners. Make sure you also put white sites in the center, and all the gauge links will take care of themselves. If we zoom out, we can put more of these building blocks or unit cells, however you want to think of it, side by side and build up the lattice. And then you start to notice that it does indeed look like it has lots of symmetry. You see 8-sided shapes, you see 4-sided shapes. If you look at it from a corner, you'll see 3-sided symmetry shapes and so on. Of course, to build a lattice gauge theory on this lattice, one question you would have is, what is the elementary plaquette? And it turns out that the smallest closed path on this lattice is a 10-sided path. Now, that might sound like a lot of sides on your elementary plaquette. It would be a lot nicer if we just had 4 sides, like a standard unit cell in a cubic lattice. A plaquette would have 4 sides. But don't forget, in 3 dimensions, you'll have to do some version of point splitting to fully define the lattice. And in that case, it's going to effectively be as though you have a 10-sided plaquette as well. So the 10-sided plaquette, maybe you can see it outlined in black. It has a certain shape. Whoops, it disappeared on me. Let's see if I can bring it back. If we look at this from different directions, you'll notice that the plaquette does not lie in a plane. It is truly 3-dimensional, and all of the plaquettes have this same shape. They're just oriented differently depending on which sites they're going through.
Really quick question. Are there 3 independent orientations? So there's magnetic field pointing in 3 directions potentially?
Yeah, great point. In fact, there are 6. And that perfectly leads me to the next slide. Jump in if you have follow-up questions, but yes, this is exactly where I want to go. So maybe we can get to the next slide and see if this is what you were also having in mind. If we think about these elementary plaquettes and we start counting them, which you're already anticipating, here's a picture. So I can draw 1 plaquette. If I start at this white site and I go around the closed path, green, yellow, magenta, cyan, green, red, yellow, cyan, magenta, and red, I'm back. So that was 10 sides right there. And if I were thinking carefully, I'd notice, oh, I guess I said red twice. I said cyan twice. I said every color twice except blue, which I never mentioned. There is no blue in that path. And so you can actually define the plaquettes by which color is absent. There's a non-blue plaquette, there's a non-red plaquette, there's a non-green plaquette. And so each of these 6 colors is left out once, and there are 6 plaquettes. Every other one happens twice, which is no accident because it's a closed path. And so if I wrote down the expression for my non-blue plaquette, it would be the trace of the 10 sides of the plaquette. We would start with white and go in the green direction. And then we would start at white plus green and go in the yellow direction. We would start at that point and go in the magenta direction. There are 5 capital U's and 5 capital U daggers, so that we go right around and end where we started. Each capital U has this familiar form from lattice gauge theory. There is a gauge field at a certain site pointing in a certain direction. And so our next job is going to be, let's Taylor expand this plaquette in powers of the lattice spacing so that we can compare it with the continuum expression. Probably you'll want to do this on a longish piece of paper, or maybe you'll want to do it with some software help. Here is the result that you'll find. If you take that non-blue plaquette and add the others as well, so you have 6 in total, and you add them all up, the result is 12, plus no term that's linear in the lattice spacing, and nothing quadratic and nothing cubic. There's this quartic term, which looks very familiar. It's the term that you were expecting to see. This is exactly the structure that appears in the magnetic terms of the continuum Hamiltonian. So I wrote the continuum Hamiltonian down here just to remind you, and here is the expression that we have found as the sum of the plaquettes. Of course, there are even higher order terms in the lattice spacing. They will all become unimportant as we take the continuum limit. And so the final step is just to change these integrals into summations on the lattice. And then we'll have the lattice Hamiltonian for the triamond lattice. And here it is. The coefficients out in front just came from changing integrals to sums. And you see, again, the way we think of all the plaquettes on this lattice is we really think of it as a cubic lattice with these white sites. And then we just have 6 different kinds of plaquettes at every white site. So this sums over all the plaquettes in the lattice. And here, for the electric terms, you're summing over the links in the lattice. And because we're working in the electric basis when we write down this Hamiltonian. And so this ends part 2 of the talk. We've arrived where we want it to be. We have a nice lattice with a lot of symmetry. It fills 3-dimensional space, and there are only 3 gauge links touching each site, so that the quantum state is defined fully by just labeling the values of the gauge links. So the final little part of what I wanted to present to you is part 3 here. Let's just look at a single unit cell, just the smallest instance of this triamond lattice that I could imagine, and see if I can really have my intuition firmed up. So this is what 1 unit cell looks like. Once again, it has 3 gauge links at every site. Notice, for example, here's a magenta link coming and arriving at the wall, but we have periodic boundaries in all directions. So this magenta link is coming over here and touching this blue site. So at this blue site, there are 3 links, they're in a plane, and they're 120 degrees apart. This always happens. So this will be our periodic lattice, just 1 cell, 12 gauge links. And if you look for the plaquettes, you will notice, for example, there's a plaquette here, or at least part of one, but then we run out of real estate and we can't finish it. It should be over here, finished in the next unit cell. And since we have a periodic boundary condition, that other half of the plaquette starts at this blue site at the opposite wall and goes like this up to the corner. So we have the whole plaquette is just wrapped around inside the unit cell. And notice that this plaquette is a non-yellow plaquette because nowhere are we touching a yellow gauge link in this path. Interestingly, though, it touches this blue link twice. We have such a small lattice that this blue link is actually the leftmost link in the plaquette, and it's also the rightmost link in the plaquette. This one's touched twice. So this is interesting because if you said, well, let's make a maximal truncation of our gauge theory, we'll allow just 2 quantum states. J could be 0 on any link, or J could be a half on any link, and those are the only 2 options. If we do that, then when you apply the plaquette operator, this blue link changed its J value, but then it changed it back again because we touched it twice. So in fact, this blue link doesn't change its J value at all. And now you realize the non-yellow plaquette also happens to be non-blue in this very, very small lattice of a single unit cell. The same thing works for non-green and non-cyan. They're the same. And non-green and non-magenta are the same, and non-red and non-cyan are the same. So the Hamiltonian in a single unit cell is the electric term plus just 3 plaquettes instead of 6 because of this special situation. So suppose you want to write this down in a form that you could actually run on a quantum computer. You want to use Pauli gates to build a Hamiltonian operator, Hamiltonian matrix. The electric part, you simply want to add up all the energies for the gauge links that don't have J equals 0, because they contribute 0 to the Hamiltonian. So here's just a projector that keeps track of, that provides a 1 for all the links that are J equals a half, and it provides a 0 for the links that are J equals 0. And the coefficient is the one we remember that gives the correct normalization. We're summing over all 12 links in the unit cell. And then down here we have a magnetic term. This is where you're applying a plaquette operator. So here are the bit flips all around the perimeter of the plaquette, flipping all those bits. That's what a plaquette operator does. And the coefficient is a couple of projectors added together to make sure that the spectators, when they have certain values, we need a certain coefficient. That's what's happening here. So this is the non-blue, non-yellow term in the Hamiltonian, but the other terms are identical. You just change the colors appropriately. So you could go ahead and run something on a quantum computer now. For example, you could use the variational method to find the ground state. So you could write down a variational circuit. Those of you who are used to doing VQE will look at this and say, this does not look very much like a generic standard VQE circuit. And it certainly isn't. We made this choice on purpose to point out that there's a high degree of symmetry in the unit cell. So in fact, you can find the ground state with what is effectively a 2-qubit circuit. The top 2 qubits here have a variational parameter and various rotations and C0 gates connecting them. But once you've set up these 2 qubits, all the other qubits inside the unit cell, all the other links, they're just directly affected by C0 gates, connecting them with what you've done in the top 2 qubits. So if this circuit successfully finds the ground state, then this must be telling us something about the symmetries in the unit cell, and it does. So here's an example. We just ran this on the IBM QASM simulator rather than on actual qubits. And by varying the single variational parameter, which is theta, you can arrive here at the minimum somewhere around 0.2, 0.3 is the minimum. And this gets the correct ground state energy, which is the horizontal dashed line. So on the next slide, I'd just like to say a little bit more about this. Why is it that this circuit gave the correct answer, and how is it that such a simple circuit works? So the periodic unit cell that we've been studying, where J is not allowed to be bigger than 1/2, there are 12 links. Each one gets a qubit. It's either J equals 0 or J equals 1/2. So there are 4,096 basis states. But Gauss's law says that at any site on your lattice, color has to add up to 0. All the incoming color to that site has to add up to 0. That means only 32 of the 4,096 basis states actually obey Gauss's law. And most of those cannot contribute to the vacuum. They're in different topological sectors. They have color flowing around one boundary and back in from the other side. And so it's actually just 4 states that provide the ground state for this unit cell. 4 is a very small number, so I can just write them down. It's the bare vacuum, where everybody's set to J equals 0. It's the single non-red, non-cyan plaquette, or this plaquette or that plaquette. And that's it. If you, for example, start with the bare vacuum, you apply the first plaquette, and then to that answer, you apply the second plaquette. It's equivalent to applying the third plaquette. You don't get a new state. And so this explains why, with just 4 states, we could have essentially a 2-qubit circuit and see the result. Let me mention in passing, though, that this is all useful, even if you want to go to larger lattices, because, for example, this note, applying 2 different plaquettes is equivalent to applying a third. This is true in the unit cell, but there's actually a version of this that is true beyond the unit cell as well. And so this is the kind of thing that we can learn by studying a unit cell carefully. It will help us when we go beyond just a unit cell to a larger triamond lattice. So if you do want to think about going to a larger lattice with 2, 3, 4, 5 unit cells, however many you want, you will, of course, have 12 gauge links inside each unit cell, so 12 times n in total. And it turns out that 4n minus 2 of those will be able to contribute to the interacting vacuum. Okay, so let me just wrap up with a very simple concluding slide. First of all, self-mitigation is a method that works well for imaginary time evolution. And we kind of like this graph since it shows such a dramatic difference between the before mitigation, which is headed upward, and the after mitigation, which does a nice job of finding the correct result. And then on the right side, the triamond lattice, it has a high degree of symmetry. It's an easy way for you to do bookkeeping and keep track of what your quantum numbers are simply by drawing the picture and showing the J values. And perhaps it's an interesting option for going to larger three-dimensional lattices. Thanks very much for your time. I appreciate it. And if you have any extra questions for me, go ahead. I'll try my best.
Randy, thank you very much. This is a very clear and illuminating presentation. Now we can have some questions. IQuS.
Yeah, thanks, Randy. This was a super insightful talk. Really enjoyed myself there. I was wondering for the 3D triamond lattice, have you thought about what you need to do to include matter? I mean, it seems to me you can't have matter on every side. They would have to hop at least 2 links to have the same dependence on lattice spacing than the magnetic term has to have in the continuum limit. Have you thought, well, if you get some interesting dispersion relations maybe of those fermions?
This is not something we have explored in any detail, but I would love to do so. Yes, that's a fantastic direction to think, but I don't have anything useful to say. Sorry.
Other question? Okay, Randy, I have one about the triamond lattice. So in the original square lattice or cube lattice, I have 3 parities, like along the X, Y, and Z directions. Right, just flip all the vertices. How does that work in this triamond lattice?
So you want to look for reflection symmetries in the triamond lattice?
Right, reflection for each axis.
Right. So something I didn't mention, but it is good to keep in mind, there are actually 2 versions of the triamond lattice, one that is effectively left-handed and one that is effectively right-handed.
Mm-hmm.
And so there is a reflection that will take you from one to the other. And that's something we'll have to be aware of. Typically, we would make a choice. You would choose, say, the left-handed lattice. And if you look at this, I don't know if you can tell from the picture on the screen, but as you go from one site to another, inside the square in the center, for example, you're climbing a staircase sort of toward the camera or down in toward the camera. And that's where you see this chirality happening.
Mm-hmm.
And so that's something we'd have to pay attention to if you wanted to talk about reflection, direct reflection in the X, Y, or Z axis. There is this opposite triamond chirality that you would discover.
I see. And these 2 different chirality sectors, do they couple with each other in any way, or they're kind of completely separated from each other?
The way we're imagining using the lattice is that you simply pick one. You choose one, that is your lattice. You do your entire calculation on that chirality, and the continuum limit won't care which one you chose. And you could have chosen the other one, but you'd never need them both.
I see. I see. Because somehow I'm thinking about what you just described. Like I rotate around that going inward the screen. If I think about an electric field winding around, right? So I have an electric wave, they're propagating inward to the plane, but somehow they only have one chirality. They don't have the opposite. So you're saying that that kind of artifact will be gone in the continuum limit.
Yeah, I agree with you. It's this interesting situation where you and I are used to talking about X, Y, and Z components of our fields. And I feel like a very Cartesian person. And this lattice that we're looking at has a symmetry that doesn't really think in terms of X, Y, and Z components.
Mhm.
For example, when I look at this lattice, it has many, many sites in it, and it has exactly 4 planes, right? At every white site, there's a certain plane. All the white sites have the same plane. All the green sites have a different same plane, and same for red and same for blue. And so if I want to talk about X, Y, and Z components, I can calculate those components from this lattice, but maybe they're not the natural components to think in terms of. I should also mention, I know this isn't really what you were asking, but I'll just say it for fun. We colored all these points and all these links with colors. But in a sense, the symmetry might be even more dramatic if everything were black links and black sites. Because notice that if you look at this lattice from the perspective of a white site, and then instead you look at it from the perspective of a red site, it looks exactly the same.
Are you pointing on the screen? We didn't see your mouse cursor moving. Sorry.
No, I wasn't even helping you by pointing on the screen, but that's a great idea. I should be pointing on the screen. If we were at this white site, and then someone else were standing at this green site, the lattice looks exactly the same because you're standing at a plane where there are 3 points equally spaced away from you, 180 degrees, and the person standing on the green site sees exactly the same thing. There's this sort of corkscrew symmetry on the lattice where if you move from one site to another, the lattice looks exactly the same. It's simply been rotated from one plane to the next. So there's this whole symmetry that we wouldn't be accessing if we talk about XYZ coordinates the way we typically do. But we could, if we wanted to, we could.
Sure, we can do the projection onto the regional lens. Yeah,
That's right.
I see. Okay, thank you very much. Any final questions? Nikita?
I have a question about the self-mitigation technique. So have you seen that the technique works worse when you make the trotter step larger?
That's an interesting question. When you say the technique works worse, of course, my answer will be less accurate if my trotter step is too big. But are you suggesting that maybe actually the mitigation itself is not as effective on a larger step?
This is something that I've seen, and I think it has to do with basically the state that you get after doing 2 trotter steps forward versus 1 trotter step forward, 1 trotter step back is just more different for larger step sizes than for smaller step sizes. I was just wanted to see if you saw that also.
Aha. I cannot say that I have noticed that, but thanks for mentioning it. That's a great insight. Yeah, I appreciate that.
Yeah. Any final questions? Also from online participants? Francesca, you look like no. Okay. Okay, I didn't see questions for the chat. So let's thank Randy again